The pathogenesis of obstructive lung disease results in reduced airflow through the airways. This may occur due to degraded elastic properties of the lung parenchyma, such as in emphysema, increased airway smooth muscle tone in asthmatics, or excess secretions within the airway lumen in patients with chronic bronchitis, bronchiectasis, or cystic fibrosis. If we examine a volume time trace, we have time here on the x-axis and volume here on the y-axis. Now let's add a typical trace of someone with obstructive airway disease. As you can see from this volume time trace, the time component on the x-axis is longer than would be expected for a normal subject, despite a normal total volume expired. When assessing subjects with obstructive lung disease, the FEV1 is typically reduced. The magnitude of this reduction, usually as a percentage of the predicted value, defines the severity of airway disease. The general expectation is a relatively normal FVC. The flatter gradient of the curve represents less air expelled per given time unit, or in other words, less air is blown out for each second of effort. This is similar to emptying a bottle of water through different sized nozzles. The bottle with the smallest nozzle represents those with airway disease. The water takes longer to empty out. The significance of this is that for some patients, the forced expiratory time, or FET, may extend to well beyond 15 seconds. The volume expired in the first second, or the FEV1, now has quite important significance as a marker of airway patency. To quantify the degree of airflow obstruction, we must mark and record the FEV1 value. The same must be done for the FVC. When dividing the FEV1 by the FVC, this gives us the FEV1 to FVC ratio. When assessing subjects with obstructive lung disease, the FEV1 is typically reduced. The magnitude of this reduction, usually as a percentage of the predicted value, defines the severity of airway disease. However, in subjects with severe COPD, a true FVC may not be achievable, as cessation of flow, represented as a plateau in the volume time trace, doesn't always occur. This may lead to an underestimation of the FVC, and care must be taken, particularly when the FVC falls below the predicted lower limit of normal. An abnormally low FVC in an obstructive subject may not necessarily indicate a superimposed restrictive disease, as a normal or elevated TLC may exist. TLC, of course, cannot be measured by spirometry alone. Increased air trapping and an elevated RV will effectively result in an equal and opposite reduction in the FVC as airways disease progresses. Bronchodilator therapy, on the other hand, may increase FVC as lung compartments that were previously inaccessible due to airway closure now become accessible as the airways supplying them dilate. In this case, bronchodilation results in an increased FVC and an equal and opposite reduction in RV. Nevertheless, as a rule of thumb, FEV1 to FVC ratio below 0.7 suggests airway obstruction. The ratio generally declines with airway obstruction severity. In severe cases, it may drop to less than 30%. However, when assessing disease progression, in cases where the FEV1 to FVC ratio does not change, a drop in absolute FEV1 and FVC values will also indicate worsening disease and likely increased air trapping or superimposed restrictive pathology. As you can see in this subject, whilst the FVC is relatively normal, the FEV1 is reduced, which of course brings down the FEV1 to FVC ratio. Even if the FVC drops due to air trapping, the FEV1 to FVC ratio will still be abnormally low. In subjects with airflow obstruction, it's expected that the FVC will be less than the RVC. Physiologically, this is due to greater pressures compressing the floppy airways during a forceful expiration, or in other words, excessively reduced transmural pressures causing airway collapse.